All right, let's get started. Thank you all for coming and for being on time. So we're going to start on time. We're almost on time. Wonderful to see so many people here. I'm Julia Stojanovic, and it's my pleasure to present our speaker, Amir Gilad. So this is a research seminar that CUSP is organizing together with the Center for Responsible AI, and that's why I'm presenting. Amir is a postdoctoral researcher in the database group at Duke. He received his PhD in computer science from Tel Aviv University. He works on developing tools and algorithms that assist users in understanding and gaining insight from data and the systems that manipulate that data. His research relates to classic database tools such as data provenance, as well as natural language processing, causal inference, and privacy. And Amir is a recipient of the VLDB Best Paper Award, the SIGMOD Research Highlight Award, and the Google PhD Fellowship for Structured Data and Database Management. And we're really fortunate to have Amir here in New York because in less than a year, in September, he will be joining the faculty at Hebrew University in Jerusalem as assistant professor. So please, Amir, and if you have any clarification questions, feel free to ask in the middle, but please keep your major questions until the end.
Thank you, Julia. And I'm really happy to be here. Again, my name is Amir, and today I'll talk about the trade-off between explainability and privacy in databases. So this talk is going to focus specifically on that. So there are many examples of the need for explanations, both coming from industry and coming from academia, including new standards that encourage companies to provide explanations for their decision-making processes to gain better transparency and allow users to understand why they made their decisions. So specifically, when we talk about explanations in databases, we can talk about two types of prevalent explanations. So the first one is detailed explanations for each one of the results. So let's take an example. Let's say James and Brenda are two users, and they both see an ad for a dance music album. Now they can ask, why was I shown this ad? Now, the system can then provide an explanation which is individualized for each one of them. So in this case, for James, it's going to be your hobby is dance according to Facebook, and it was published on Reddit that you're interested in music. For Brenda, it can be a different explanation, which is personalized for her, which is your hobby is dance according to LinkedIn, and you're interested in music according to Facebook. So the second type can be called summarized explanations. So let's take again an example. Let's say I have data about individuals, their income, marital status, and other attributes as well. Now the user wants to ask first, let me group the people according to their marital status and see what their average income is. And the income here is normalized to be between 0 and 1. So here's the result shown on the left. And the user can then ask, why do married people make more money than the people who are never married? So again, a prevalent explanation approach in databases is to show something like people in managerial roles influence this gap, or people with a bachelor degree influence this gap. And intuitively, what that means is that if we take the database, remove all the people with this occupation as managers, then the gap between the two groups in terms of income would be decreased. And the same thing goes for bachelor degrees. So these are the two prevalent approaches for explanations. Now let's talk about the second subject of this talk, which is privacy. So when I talk about privacy, I can talk about two different aspects. The first aspect is to protect a query or an approach. So let's say I'm a company, I've developed some kind of proprietary approach to target people for ads. So I don't want this query or this approach to be leaked in any way. The second aspect is to protect the data. So if I'm, for example, a governmental agency and I collect data about individuals, I don't want the specific data about individuals to be leaked, but I still want to allow researchers to perform some kind of analysis about the data and not keep it completely private. So naturally, explanations in addition to the results leak more data. So they compromise privacy even more, but we would still like to have some way of providing. So the goal of this talk is to show you that we can provide explanations under privacy. So we can do that while maintaining privacy, but we just have to use some custom techniques and be a bit more careful in terms of how we do it. So I'm gonna split this talk into two parts. In the first part, I'm gonna talk about providing personalized explanations or detailed explanations while protecting a proprietary query. And this part of the talk is based on our work that was published in SIGMOD and ICD. And in the second part, I'm going to talk about providing summarized explanations while protecting the data itself under differential privacy. And this work will be published in VLDB. And lastly, if we have time, I'll talk about some interesting future directions. So consider this setting. Some kind of company or organization perform a query over a database, and then they decide, based on the results of the query, to show some results to the user or to show an ad, and then the user can also ask for an explanation. So this scenario has been addressed to some extent by large companies in industries such as Google and Facebook. And we can think about it in terms of our example again. So again, we have James and Brenda. They both see an ad for a dance music album, and they want to know why they were targeted for that ad. So each of them get a personalized explanation. Now, here's a way to model this. So here's a small database that kind of models what we're looking at in this example. So this database consists of 3 tables. The right table contains information about people, their person ID, name, and age. The second table, the middle one, shows for each person ID their hobby and the source from which it was obtained. And the leftmost table shows for each person ID their interest and the source from which it was obtained. So now reconsider these personalized explanations. If James and Brenda are friends and they share these explanations, they can quite easily understand the general criterion for targeting people for ads, right? So in general, it will be if your hobby is dance according to one source and you're interested in music according to another source, you're probably going to get targeted for that ad. And in fact, in our previous work, we've showed that in most practical cases, it's enough to have just a handful of these explanations to be able to reverse engineer the query. So this is not good for the company that wants to keep the proprietary query private. So instead, if we consider a more abstract version of the explanation, then it might be more difficult for them to reverse engineer. So in this case, instead of telling James specific information, we can say, you were shown this ad due to some information from Facebook, and it was published on Reddit that you're interested in music. And to Brenda, we can say, you were shown this ad due to some information from LinkedIn, and you're interested in music according to Facebook. Then we've made the explanation a bit more vague, but now it's more difficult for them to reverse engineer the query. So this is what we want to strive for. So let's talk a bit about our model. So reconsider the database tables that we've just seen. So below them is a conjunctive query. So this query intuitively tells us how to target people for ads. So it will return a person's ID if their hobby is dance and according to one source, and they're interested in music according to another source. So technically, this query contains 3 predicates on the right-hand side. And if these predicates are assigned tuples from the database that satisfy them, then this query will return an ID of a person. So let's talk about the way we model the explanation now. So we use, in this work, we use data provenance, which describes the data that was used for the computation process and sometimes even the computation process itself. Now, provenance has been studied both in terms of its models, tracking, storage, and applications, and in particular for explanations by multiple previous works, and it's considered the gold standard for database explanations. So let me give a quick example of data provenance. So here again, we have the database and the query that we've seen. So if I assign the tuple whose ID P1 is P1 to the first predicate, the tuple whose ID is H1 to the second predicate, and the tuple whose ID is I1 is the third predicate, I would get the input 1, which is James's ID. So I should target James for that add. And the provenance of this result would be the 3 tuple identifiers. And in this case, we use the product of the tuple identifiers, which is an algebraic model that was proposed by previous work. So now, as we mentioned, James and Brenda can share their explanations. So how do we model that? Well, we can model that using a table, or what we call a provenance example. So in this provenance example, we have 2 rows that model the explanations for James and Brenda. For each row, we have the output generated by the query and the explanation. So this is what the users see. They don't see the query, but they see the explanations instead. Okay, so now we know what is provenance and what is a provenance example. So let's talk about the notion of provenance abstraction. The provenance abstraction has been proposed by previous work in terms of, in order to reduce the size of the provenance. So it was supposed to make the storage of the provenance more efficient. In our setting, we're going to use it in a slightly different way to make the explanations more vague. So again, we have the database tables at the top, and below them is an abstraction tree for this database. So in this abstraction tree, we group tuples according to their source, the source from which they were obtained. So for example, H2, H5, and I3 all 3 were obtained from LinkedIn. So their parent in the tree is LinkedIn. And we grouped Facebook and LinkedIn with social network. And this is just one example of an abstraction tree. So there can be multiple examples of such trees, even for a single database. So let's see how we use this tree. So here's the provenance example that we've just seen. So this is the original explanations. And now to make them more abstract, we replace tuple identifiers with their ancestors in the tree. So now instead of having in the explanation all of the information conveyed by the tuples H1 and H2, we replace them with Facebook and LinkedIn. Okay, so what does this give us? What is this abstraction meant for? So now there are a few ways of interpreting this provenance, right? Because for Facebook, we have a few tuples that can be, that are its children. So we can basically replace Facebook with each one of them. And the same goes for LinkedIn. So now there are several queries that will generate provenance or generate the explanations that can be abstracted to this form. So now it's unclear which is the correct form, right? So this is a way of making the original query less obvious. So now we know that James and Brenda are intelligent users, and we can't fool them with just any set of candidate queries that will generate this provenance. So we have criterions to make this this set of candidate queries more believable. So the first criterion is that the queries need to be connected. So there needs to be some connections between the criteria that the query requires. So formally, it means that each predicate in the query has to share a variable with another predicate in the query. In this example shown on the slide, we see that all of the predicates share the variable ID. Then the query also needs to be consistent. So that just means that for each of the rows in the provenance example, the query will generate the provenance that can be abstracted to the provenance in that row when generating the output in the same row. And third, the query needs to be inclusion minimum. So that means that for each candidate query, we cannot have another consistent query that is subsumed in it, that is smaller in some sense. And that intuitively tells us that each query is a tight criterion for generating this provenance. So if we have k candidates that meet these criteria, then we say that the privacy of this abstract provenance example is k. Or in other words, the proprietary query cannot be distinguished from k-1 other candidate queries. Okay, so now let's talk about the other side of abstracting explanations. So even though, yes?
It's just like a small clear event metric sense, provenance query. What is the object P1?
So P1 is a tuple identifier.
So what do you mean by, you said a product, what is that? Is it literally, it's not like literally.
So each tuple has a unique identifier, and the product is just an algebraic way of representing a provenance. So you can represent it as it's called the semi-ring model, and for the semi-ring model, you can represent it as a polynomial, where each monomial corresponds to an assignment. So here we have one assignment that satisfies the query. So this is just one monomial, which is represented as the product of the tuple identifier.
I see.
The idea is that at the end of the day, you just return to the person basically just a tuple of these three things, right? Or is that not?
Yes, you can think about it like this, but you can also use, for example, natural language templates to translate this technical information into natural language, which is the example that I showed. Okay. So this is very similar to k-anonymity, just for queries, right? If you know k-anonymity. Okay, so whenever we make the explanations more abstract, we gain privacy. There are more queries that can generate the provenance, but we also lose information that is useful for the user and informative. So eventually, we do want to give users explanations that are informative and give them some added value. So what we want is to find a way to quantify this loss of information. So reconsider this abstraction tree, and below it is an abstract provenance example. So here we replaced I1 with Reddit. And now there are 4 ways of making this provenance concrete, right? So each one of the specific tuples below Reddit is an option for the real provenance. Now, if we have a probability attached to each one of them, to each one of the possibilities, then we have a probability space, and we model the loss of information simply as the entropy of this abstraction. So this is then well defined if we have a probability space. And now we are ready to define the problem that we want to solve. So we want to find the optimal abstraction. So what do I mean by the optimal abstraction? So given an abstraction tree, a provenance example, and a privacy threshold, what we want is an abstraction that would give us privacy at least k, and we'll have the minimum loss of information. So intuitively, we want to protect the proprietary query, but by making it indistinguishable from k-1 other reasonable candidates, and we want to minimize the loss of information over all other abstractions that achieve that. So the explanations are as informative as possible. So it can be shown that this problem is NP hard, and this is by reduction from vertex cover. So to nevertheless compute this optimal abstraction, we do iterate over all possible abstractions, but we have some practical optimizations that allow us to have a solution that is scalable and can run in reasonable time. So here's the abstraction tree that we've seen again, and below it is the concrete, the original provenance example. Now here are three ways of abstracting it. So, for example, we can disqualify the first one quite easily because it does not meet the privacy threshold, and we have an optimization that allows us, in most cases, to understand that without actually generating the candidate queries. We can also disqualify the middle abstraction because it does not minimize the loss of information over all abstractions that achieve the privacy threshold, and we know that because we generated the left abstraction that has lower loss of information. So essentially, we have a lot of optimizations that allow us to achieve a good runtime. So as part of the evaluation of this approach, we've conducted a user study that included 12 participants. We've divided them into two equal-sized groups, Group A that was shown the original provenance and Group B that was shown the optimal abstraction. And we've divided the study into two parts. So in the first part, we've asked them to reverse engineer the original query. So as we can see, all of the users from the first group were able to reverse engineer the query, while none of the users from Group B who saw the abstractions were able to do that. And in the second part, we asked users 10 hypothetical questions about the explanations and about the database that relate to the explanations. And we ranked their answers as correct or incorrect. Now here we did not see a significant difference between the answers that were given by Group A and the answers that were given by Group B. So this indicates that the explanations remain informative even when abstract. Yes.
Can you say a little bit more about the data that was used?
We used, in the study, we used IMDb.
The whole thing?
I don't remember if it was the full database. I think it was a subset of the database. Yeah, I think specifically, we looked at specific actors and directors and their movies. So for example, I don't know, I think Kevin Bacon was there and the other actors. But yeah, we did not consider everything. Yes.
Can you give me an example of what it would mean to like recover a query in this context? What does a query look like here?
Yeah, so a query looks like what we showed in one of the previous slides. So this is a query, for example. This one.
So find all people who.
Yeah, return all people whose hobby is dance according to one source and whose hobby who are interested in music according to another source.
Okay.
Yes, exactly. Yeah. So in terms of scalability, we've examined our approach in terms of runtime for different parameters. And this is showing the scalability as a function of the privacy threshold. So this was K in our problem definition. And this is shown for TPCH and the IMDb datasets and their queries. And here we can see that as we increase the privacy threshold, the scalability remains pretty good. So it does not increase the runtime significantly. Okay, so to summarize this part, what we wanted to do was to provide, I'll just finish this slide. So what we wanted to do was to provide a provenance-based explanation, so detailed explanations for the query results while not revealing the actual query. We've used provenance abstraction and this privacy criterion based on k-anonymity for queries. And the trade-off here is that the more privacy I want, the more vague the explanations become and probably less informative. Yes.
So it sounds like you've got basically a branch embedded algorithm to solve an inherent problem. So your runtime can still be exponential in some way. And I'm just trying to.
My runtime is yeah. So complexity-wise, this algorithm that we have is exponential, but
What is exponential? Is it the depth of the tree?
why
you're seeing pretty good.
So actually it's exponential in the number of leaves in the tree, I think. So yeah, but in practice, since we have these different optimizations that sort the abstractions, for example, we prioritize computing the loss of information, which is significantly easier than computing the privacy of each example. This allows us to disqualify a lot. Yes.
Is there a reason that you used a k-anonymity frame for this, given the sort of weaknesses that k-anonymity has for external uses of information instead of say something like that?
So there's no particular reason. So we had to come up with a criterion for queries, and I'm not sure how would differential privacy look like for queries. I mean, I'm not sure what is the.
So,
For example,
I'm just going to ask that we keep conceptual questions to the end, right? So for now, just clarification, because there's another third here, if that's okay.
Yeah, but I mean, it's definitely an interesting question for future work to come up with a criterion that would keep queries private under differential privacy. Yeah. Okay. So now I'm gonna what?
you've got a differential privacy thing coming, right? Yes.
Yes, but this is going to be for data. Yeah, so now this is going to be a different setting where we're going to talk about summarized explanations for queries while protecting the data itself under differential privacy. So this is the general scenario. A user asks a query from a system. This system then queries the private database. And since we use differential privacy, the results returned to the user, even the initial results, are noisy. So the user then sees these initial results, and they can ask a question about the results. So why am I seeing this? Or why is this relationship between the two groups this way? Why is one group larger than the other? Now, our goal is to provide explanations for the users. So this scenario without privacy has been considered by previous work. So let me first talk about the scenario without privacy. So again, consider the example where we have individual data about people's income, their marital status, and other attributes. And the initial query was to group them according to their marital status and get the average income normalized between 0 and 1. And the user then notices a significant gap in income between the people who never married and the people who are married. Then they may ask, what is the reason for this gap? So previous work has developed an approach for providing explanations for such scenarios. So in this case, individual tuple explanations like we've seen in the previous part will not suffice. And they're probably only confused because there can be many tuples that influence the results. So the idea is to summarize them using predicates. So here you see an explanation table that contains predicates, their rank. So in this case, they're just ranked, and their relative influence, where the relative influence is measured using a dedicated function. Now, as we mentioned initially, the predicate occupation executive managerial intuitively tells us that if we were to remove all of the tuples in the database with occupation executive managerial, then the gap between the two groups would be narrow. So now let's consider this scenario with differential privacy. So with privacy, we can't show the original results or the actual results to the user. So we have to add noise to the results. So here you can see the visible results shown to the user. And in the gray column, you see the actual result, the private ones, but the user cannot see them. So there's a gap here between the actual results and the private results. Now this leads to two main challenges. So the first one that we can notice is that the relationship assumed by the user in the question may not be the actual relationship between the groups in the private data. And it can be a result of noise. So in our example, it might be the case that in the private data, actually, people who never married make more money than the people who are married, right? And we're just seeing this gap in the visible results due to noise. And the second problem, or the second challenge, is that to provide these explanations that we've seen in the previous slide, we can't directly do that without violating differential privacy. So we have to come up with some new techniques and new mechanisms to allow us to do that under differential privacy, and these do not exist or did not exist. So due to these challenges, our system DP-Explain works in multiple phases. So in the first phase, the system first tries to validate the user question or validate the relationship assumed by the user in the question. So to do that, it generates a confidence interval of the difference between the two groups. So in our example, this is going to be the confidence interval of the difference between the income of married people and the income of the people who are never married. Intuitively, if this interval includes 0, then it might be the case that in the private data, the relationship is reversed. If this interval does not include 0, it strengthens our assumption that actually this is the true relationship, and the relationship assumed by the user is not due to noise. So in this example, you can see that we did not include 0 in the interval, which intuitively tells us that probably people who never married make less money than people who are married in the private data as well. So then in the second step, DP-Explain generates an explanation table. So this is very similar to what we've seen in one of the previous slides, but now we have these different steps that we have to go through to guarantee differential privacy. So the initial explanations have to be chosen in a noisy manner to guarantee differential privacy. The rank is a confidence interval instead of a single rank, again, to satisfy differential privacy. And again, for the same reason, their influence is provided as a confidence interval instead of just a single number. Okay, so let me say a quick word about differential privacy. So differential privacy is considered the state-of-the-art technique for preserving the privacy of individual data and sensitive data. And it's been adopted by multiple organizations and companies and governmental agencies, including the IRS and the US Census Bureau, due to its theoretical guarantees. So let me give an intuitive example of the guarantee of differential privacy. So here we have two databases, D and D prime, that simulate information about hospital patients. In D, we have the patient Bob, and in D prime, we do not have the patient Bob. Now let's say that this data, both D and D prime, are given to some algorithm A that learns something about the data. Now what differential privacy tells us is that what can be learned about Bob from running the algorithm on D is very similar to what can be learned about Bob from running the algorithm with D prime. So in other words, no personal sensitive data of Bob will be leaked in any way. So how do we use differential privacy in databases in practice? So we have a query, and we also require a privacy budget. Then, using this privacy budget, instead of showing the actual result, we add noise to them to show a noisy result. Importantly, and this is something that we're going to use. Okay, so the noise is going to be proportional to the inverse of the privacy budget. So the more privacy budget I have, the less noise I'm going to add. And it's going to be proportional to the sensitivity of the query. So if intuitively, the sensitivity of the query is a measure of how much does the result of the query changes for similar database. If the result is a lot, then we have to add more noise. If the result is just a little bit, then less noise would suffice. Yes.
So the budget is small if we add a lot of noise?
If the budget is small, so the budget is part of your input. So if the budget is small, you have to add a lot of noise because it's proportional to the inverse of the privacy
Okay,
budget.
the small privacy budget means I need to be very private.
Yes,
Okay.
yes, exactly. So in other words, small privacy budget tells you I cannot reveal much from the actual database.
Okay.
Okay, so in light of these restrictions of differential privacy, we had to tackle and come up with an approach for all of these components. So first, as we talked about, we wanted to find the user question interval under differential privacy. Then we had to develop a low sensitivity influence function. This is a very important component because we had to use it for finding the actual predicates that we're going to show in a noisy way. So this is using the influence function, finding the interval of the rank, again, using the influence function, and finding the interval of the influence, of course, which obviously uses the influence function. So we were able to devise a mechanisms for each of these components, and we have a formal guarantee that says that given a group by query and the user question that compares two groups like married and never married, Explain guarantees differential privacy. And you can find the full details of the mechanisms and the theorems and their proofs in the full paper that's in arXiv. So here, due to time restrictions, I'm going to focus on two challenges: developing an influence function and finding the rank interval. Okay, so let's talk about how we've developed a low sensitivity influence function. So there's a well-known work that explains outliers in query results that has an influence function. So this was our starting point. This function intuitively tells us, let's compute the influence of a predicate by computing the aggregate value of a group with all the tuples in the database, minus the aggregate value of a group with all the tuples in the database, except the ones that satisfy this predicate. And this is that not p in the second element in the numerator. This is then normalized by the number of tuples in the group that satisfy the predicate. So now there are two issues with this function in our set. So first, it only measures the difference for one group, GI, and we want to measure the difference between never married and married, so GI and GJ, let's say. Now, if we only handle this issue, then we'll get a function that has high sensitivity. So if you recall from one of the previous slides, high sensitivity means more noise. More noise means bad approximations, and that would cascade throughout our process. So we would get bad predicates, we would get bad rank intervals, and we would get bad influence intervals. So we don't want that. So that's why we make two modifications. So the first one is to expand the numerator to measure the difference between two groups. So now we measure the difference between the two groups with all the tuples in the database, minus the difference between the two groups with all the tuples in the database, except the ones that satisfy the predicate. The second modification is to bound the sensitivity. And here we add a normalizing factor for the three types of queries that we support. So for count and sum, we have one normalizer, and for average, we have another normalizer. So this allows us to get this guarantee that tells us that for count queries, we have sensitivity 4 with this function. For sum queries, we have 4 times the maximum value in the aggregated attribute. And for average queries, we have 16 times that. Okay, so now we've developed a low sensitivity influence function. So I'll talk about providing a rank interval. So here's a first try. Let's try to compute the rank of a predicate, add noise to it because we have to add noise because we want to satisfy differential privacy, and then just attach a fixed margin for that noisy result. So what's the problem with that? So again, the rank function has high sensitivity. So in other words, for two similar databases, the rank of a predicate can be very high for one database, and it can be very low for a very similar database. So in many times, because of the high amount of noise that we would have to add, we would end up with just a trivial interval that is 1 to the number of predicates that we consider, which is not a good informative estimate for the user. So instead, we use noisy binary search. So let me try to explain this somewhat complex illustration. At the top, we have the influence of all the 15 predicates that we consider, and they're ranked here according to their influence. So you can see them according to the circle. Our goal here is to compute the upper bound of the rank interval of that red circle, the third predicate. So we cannot return 3 because we want to satisfy differential privacy. So we have to get a rank interval, and we want to compute its upper bound. So what we do is we artificially lower the influence of that predicate. So instead of having it at the true influence, we lower it just a bit, and we perform a binary search. So the lower part shows you the pointers in the binary search. So in the first loop, we have 2 pointers, T low and T high. T low is at 1 and T high is at 15, and T is just showing you in the middle. So at the middle point in the first iteration, we look at the influence of the predicate at that point, the 8th predicate, and we compute its noisy influence. So this is denoted by the circle 1. So it's not exactly on the influence of that predicate because it has to be noisy, right? So it's a bit above it. Now, how do we decide which of the pointers we're gonna advance based on whether we're in the green or in the orange zone? If we're in the green, we're gonna advance T high. So we advance T high to be at 7, and then we're seeing the middle point at 4. We're computing the influence. We get the orange zone, so we're going to advance T low, and this process is done when T low and T high are at the same spot. So this is 5, and this is what we end up returning as the upper bound of the confidence interval. Okay, so the upper bound of the third predicate is going to be 5. If we wanted the lower bound, we use exactly the same procedure, but this psi is just going to be increasing the influence instead of decreasing. Okay, so as part of our evaluation, we've experimented with different use cases. So here's one of them, and this is over the census survey from 2011 to 2019. And this is very similar to the example that we used. So we had information about people, in this case, their sex, income, and other attributes as well. And the original query was to group by sex and aggregate the average income. So we got a difference between males and females in this data set. And the question was, why is the income of males larger than the income of females? So in the initial step, the system generates this confidence interval that does not include 0. So it means that probably males make more money than females in the private data as well. And in the second step, the system generates this explanation predicate, this explanation table that contains different predicates, and you can see specific race and relationship and so on that appear here. So to measure the precision of how we noisily choose the predicates that will appear in this table, we've measured also the precision at K for different parameters. So here, this is a function of the privacy budget and the size of the table. So K, the number of predicates that we end up showing. And here we see that for most of the queries, we have high precision. There are 2 queries denoted here by the purple and the orange lines that are not getting high precision, and this can be explained due to the fact that their result set is containing very small groups, which leads to higher noise from the mechanism. So just to summarize, what we wanted to do was to provide predicate-based explanations while satisfying differential privacy. we've used a custom influence function that we've developed and differential, right, and the mechanisms that satisfy differential privacy. And here, the lower the privacy budget, the noisier the explanations become. So to wrap up this talk, we had two parts. In the first part, we've talked about detailed explanations that were modeled using provenance. We wanted to protect the query, and we did that using a criterion that was based on k-anonymity and abstracting the provenance itself. In the second part, we wanted to give summarized explanations, and these were modeled using predicates. And the goal was to protect the sensitive data, where we use differential privacy and specially designed mechanisms. So there are a few interesting directions of future work. Julia, do we have time or?
Give me a couple of minutes. We want to leave time for questions.
Okay, yes, okay. So there are a few interesting directions of future work, and I'm only going to discuss 3 of them, basically. So in the first part, we've kind of assumed that we have this abstraction tree. Now, this abstraction tree can be non-trivial to generate from the data. So we can assume that DBAs and experts in the database and domain can generate these abstraction trees manually, but it can be hard to generate them automatically. We can maybe deduce them from ontology building tools that generate them automatically. But it would be interesting to explore generating these abstraction trees automatically with attributes that are good for specifically abstracting provenance and making the informations and making the explanations still informative. For the second part, we only support so far some count and average, which is very nice, but we know also that join queries, for example, can be supported with differential privacy. So we know how to display the results of join queries with differential privacy, but we cannot explain them. So expanding that class of queries that is supported is an interesting direction. And the third direction that I want to mention is that these are just 2 of the most basic and prevalent approaches for explanations, but we can also think about other approaches for explanations in databases that are very useful and are not, as far as I know, cannot be computed in a private manner in databases. So for example, there was a recent work that looked at explaining the query results using Shapley values. So this quantifies the contribution of each tuple to the query result using their Shapley value, but supporting this explanation form under differential privacy, for example, is still an open problem. So thank you, and let me know if you have any questions. Yes.
So Facebook and other companies, I know they have some of this, why am I seeing this ad?
Yeah.
So how close is what they're doing in practice to what you need in terms of part 1? And is anybody actually doing things like what you're describing, and why or why not?
So as far as I know, from my personal experience with the explanations provided by Google and Facebook, it looks like they're kind of already providing abstract explanations. So they're not showing you the specific details of why you were shown this ad. They say due to an activity in Facebook, or due to an activity due to your recent searches. So this is a form of abstract explanations. So in some sense, I don't know if deliberately or not, but they've already implemented at least some of the approach. Yes.
Yeah, so I'm curious, like from a policy standpoint, if you have any perspective on it, the fact that you're able to do explainability, could policies then be put in place to say to Facebook or Google, you have to explain this to the user, and these are like, this is the amount you have to explain this part A, and then part B is like there'd be some third party government that's actually
Overseeing this.
so that the company doesn't lie what they're saying.
Yeah.
So like for instance, like maybe they're to explain how they got the information, that would have to come out. So things like that where you're actually like making.
I think this is still in discussions in lots of for many standards and countries. I think even GDPR, for example, if you know that standard, they do not explicitly say that. As far as I know, that the companies have to explain their results, because I think it's hard to say what is the minimum standard for that. And I don't know, I mean, Julia can probably also add some information, but I don't know if a lot of companies are able to really explain what's going on in their decision-making models, in particular if it includes some convoluted machine learning process. So I don't know if that's even possible to enforce for companies. Yeah.
Related to that, I'm wondering if you have sort of a more sympathetic example than trying to protect an ad targeting spec, right?
For trying to protect what?
An ad targeting spec, which like a lot of people like would say that for people that are interested in privacy, like that's something that should be transparent, right? Like we've thought of, are there some other case, you know, that was your running example, or there's some other case studies.
Yeah. So you can think about these are kind of competing ideas always. So you can think also about, for example, I'm talking from the corporate side. So you can think about insurance companies. They don't want you to know exactly how they set their rates, or whether yeah. So it's not sympathetic. It's sympathetic to the corporates, but it's interesting to kind of mitigate this gap.
Lucas.
Yeah.
Thanks for the talk. I was wondering, I noticed you're using like concentrated differential privacy. I was wondering why you're using that as opposed to something a little more pure, more private.
Like the classic differential privacy. So we've used, this is a good question. We've used several mechanisms that I think work with this concept. So it was just easier for us to work with this.
Could you talk me through, give me a sense of like what level of privacy those row values are giving you? Like, do you have a sense? Or like, what is like the standards? Because I'm much more used to thinking about like an absolute budget than like a row budget.
Oh, so actually, I don't remember the exact relationship, but we talk about this in the paper, so you can see that one. Yeah. Oh, yeah. Yeah.
Yeah, so thank you for your talk. Sort of, I could ask a conceptual question about abstract provenance. So in your examples, the abstracted version of the provenance is like which social media sites did the information come from?
Which source?
So in an example like that, like doesn't that sort of make the explanation not a great explanation? Like if the query is meant to like estimate my income, for example, like, and the only thing you say is that the information came from my social media profile, that doesn't really say anything about why I deserve to make that much money, right?
Yeah. So that's why I think that's very related to generating these abstraction trees in a way that is kind of good and would tell you the loss of information needs to be very fine-grained measure for how much information you're losing. But as I've mentioned, this is also kind of the explanations that you're currently getting from Google and Facebook today. So the explanation that you would get is due to your previous searches. Yeah.
Yeah, actually two questions. One is for the, I mean, I'm not convinced about the advertising, the ad example, because relational databases aren't really used to produce that. Sure. So if you have like a whole pipeline with all kinds of machine learning steps involved, how would this be that?
Yeah, that's a good question. So I'm not really sure how to adapt these notions, but I assume that the concept of abstracting the explanation in some sense would be useful. In machine learning, the explanations are kind of more vague in the first place because you would get the influencing features, for example, or some kind of ranking of, I don't know, the attributes that you specifically possess to change your classification. So if the explanations are more detailed, in some sense, telling you, I don't know, it's because I didn't get the loan because my income is lower than 50,000, and I don't know, my credit score is lower than 700. So maybe these type of explanations can also be abstracted in some way. But this is an interesting direction of future work, to evolve machine learning models.
The other thing I was wondering about is how do you formalize the quality of an explanation? It's not clear to me that a detailed explanation is a better explanation. Sometimes the simplest explanation should be.
Right.
We got this result here about the different incomes because here's the database. You can see the whole database. You really want to get something simple like, well, maybe Amir Gilad number, etc. You want to have a simple explanation, but it also depends on who's asking the question. You get the ad example. If this is about me and the ad being shown to me, I want to get contact with explanation. If I'm the advertiser and want to know why was that ad shown, well, you should put higher on keywords. It like it's very much based on different aspects.
Right. So this is a very good question, because there is no standard today for what is a good explanation, even in general, not even specific to a population. So people try various approaches to get explanations, and seeing how detailed or how summarized it is one of them. And we've explored that actually in one of the previous works, where we try to summarize the explanation as much as possible, because the assumption is that if you have, for example, a lot of similar explanations, you would want to get some kind of summary for them. But there is no like benchmark for what is a good explanation.
As far as I understood, your results are not strongly dependent on noise. I'm not an expert on machine learning, but I wonder, how do you filter noise from changing behavior, because this is particularly affected by the way people change their behaviors, and how far these will affect the potential automatic development of abstractions to plugins.
Oh, so you're talking about the first part.
Yeah.
And if people, yeah, so in the first part, we do not, we do not handle noise in some sense. We assume that the database is given, and we just want to find an abstraction for the explanation. Handling noise is kind of related to the question that I answered in the talk about some kind of a criterion for queries that relates to differential privacy, which we have not developed yet, but it could be interesting. Actually, this was one of the competing ideas that we started with, but we ended up with this k-anonymity based criteria. Yeah.
In the context of your running example on the k-anonymity one, right? So, you know, you mentioned earlier, like laws like GDPR and CCPA, it would seem like the type of information that you could get and download all your data and so on would allow for the same type of augmented information that would cause problems with that. So have you done any modeling? Like you had your little experiments that are like, well, if you only have which k-anonymity holds for, if you only have the information that I've given you and there's no other information in the world, then you have these guarantees. But as soon as you open that up, it can't fall apart.
So you're saying if I have a big database, then privacy in the first part is
well, no. If so if the people that are trying to reconstruct the query, right, have augmented information, for example, being able to say download their data through a GDPR request,
yeah,
right? So they have like a list of all their interests, all the information, instead of all the other people, then they can rule out some of the queries, presumably that were given that were part of the uncertainty set.
Meaning k-anonymity doesn't work, right?
And then it would not fall.
Not sure that's true, because they can basically try to reverse engineer it even without the database I don't see how how more data will make the query easier to guess.
Because k-anonymity breaks with auxiliary information, and this is one kind of auxiliary information that would break k-anonymity in principle. You can design like a specific attack, but there does exist such an
Yes.
attack.
Okay. So yeah. So probably, yeah. Maybe this can be broken using some criterion of I don't know, attack and auxiliary information, but we did not consider it. Yeah, but differential privacy is probably a more robust way of modeling this. Yeah.
First, I'd offer like a more sympathetic example is potentially medical domain, which the hospital is required to protect certain information if you're sharing with other hospitals.
Yeah. Yeah, the specific query, need to think about it, but yes.
And then I think the question is related to one of the plots you put up with sort of performance across a set of different queries. Could you talk about like complex? Because it seems just initially I would expect that there just are certain queries that you essentially would never expect to do well because they operate on such a small group of people. So like, how did you go about choosing this set of queries for the benchmark, and like, what is some of the complexity of some of these queries?
So we've used just a different various queries that I think are not. There are no standard queries for these types of approaches. So we've just experimented with various queries that asked about different parts of the data and grouped the people according to different criteria. So there was no, I think there was no principled way, but there were some that were more complex and some that were more simple. Yeah.
So in the first part, provenance part, when under the advertiser lens or whatever, the point of the privacy here is to try to defend against collaborating users trying to reconstruct a query.
Yes.
Whatever you did, you're like surveying and experiments and everything with people. Were they allowed to talk to each other and allowed to compare their notes and they were trying to come up with a query?
So
or was it like everyone was?
So the idea was that they are shown the set of explanations. So they were not allowed to compare notes, but each of them was kind of used as the person who is trying to crack it. So
everyone was shown all the same information?
Yeah.
Okay, so everyone had the exact same information.
Yeah. So we did not give each of them a personalized explanation and ask them to think together.
Okay. Cool.
That would be a fun experiment to do, right? Actually, to follow the motivation that.
Yeah. Right. Yeah.
Are you interested in doing sort of a similar subjects experiment on the differential privacy explanations? Because it seems like trying to get at the like confidence interval of the noise ranking stuff will be a little hard for a lot of people to digest, and just like they what the user interface is. So that explanation is probably a thing.
Yes, so that is a good point. The explanations that we currently provide are more expert-oriented, and they're not completely non-expert who can look at them and say, okay, this makes sense to me. I think this is just the initial work that tries to develop this approach, but certainly I would aim for much simpler approaches, like we have with provenance, where we can translate it to natural language or to summarized explanations, or whatever we want, basically.
There are no more questions. Thank you once again.